lightning talks, and the first is by Vitalis Vosylius from Imperial College London, and he will speak about in-context imitation learning via graph diffusion.
So, hello everyone, I'm Vitalis, and today I'm going to be talking about my recent work, which we call instant policy, and hopefully you'll soon understand why we call it like that. So, I assume I don't really need to motivate the dream and the potential of robotic manipulation to people that are here. What I would say that I think that in reality we are moving towards that dream. It definitely seems so with all of the cool demos coming up. But it's still mainly driven by data-hungry behavior cloning, where we still require hundreds of demonstrations to learn new tasks for robots. So we can ask then why it's still so hard to teach robots new skills effectively and efficiently. And here I would argue that we have two main challenges. We lack the appropriate inductive biases in our representations. So learning to map images to actions is hard, and we ask a lot of neural networks to internalize all of the possible tasks, all of the environment dynamics. It's a hard problem. And second, we just don't have enough data to brute force our way to the solution. We just don't have it. So to address these challenges, we tackle the problem of in-context imitation learning and present instant policy. So in-context imitation learning uses demonstrations at inference to define the task and how it should be solved. And then the model is tasked to interpret the provided demonstrations, i.e. the context, and act upon it accordingly to solve the task that's just been demonstrated in novel configuration. So here you can see I provided a demonstration of a task that's never been seen before during training, and then the model uses that demonstration as an input and completes the same kind of task in a novel configuration. And it's quite robust to external disturbances, to distractors. Here you can see another task of folding this pair of jeans. So I provided a demonstration, and then the model looks at that demonstration, looks at what it sees now, and then acts upon it to complete the same type of task. Here is a different configuration of jeans, and it does it in a closed loop manner, always looking at what it sees, looking back at the demonstration, and acting accordingly. So how do we do this? The first thing we need to do is to choose the right representation for the problem, and in-context imitation learning has three components. So the current observation, the context, I provided demonstrations, and future actions that we want to predict. So for the observation representation, we use point cloud observations and represent the joint representation of the robot and the environment as this type of graph. Here the green nodes represent the local geometries of the object, and the collection of blue nodes represent the state of the robot. And together they jointly represent the state of the robot and the environment. Now if you take a sequence of such graphs, then we can define a demonstration trajectory or any future actions. And then when we put all of the components of in-context imitation learning together, we get this sort of a joint graph representation that jointly expresses the provided demonstrations, here on the right, the current state, and all the future actions. So this is a structured kind of representation of all the components. It has a clear information flow to it, and this kind of allows us to tackle the in-context imitation learning efficiently and effectively. So in order to generate actions, now what we want to do is generate these types of graphs, learn to generate these graphs. And we do so by framing in-context imitation learning as a graph generation problem using diffusion models. So we only adjust the parts of the graph that represents the low-level actions. In this way, we can implicitly model the conditional distribution of actions. So at training time, we start with the ground truth actions, add a little bit of noise to it, construct our graph representation. Then we feed it through a graph neural network, which says how each node in our graph that represents low-level actions needs to be adjusted such that that noise is removed. So we add noise and learn how to remove it. And then during test time, we start with a random action sampled from a normal distribution and iteratively refine them until they represent our desired actions that the robot can then take. So in this case, move towards the toilet roll. And this allows us to very effectively structure the problem and efficiently learn it. So the next question is, where do we get the data to train this graph diffusion from? So for this, we can first look at the behavior cloning setting, where we learn the mapping between observations and task descriptions to robot actions. So in this setting, the weights of the neural network need to encode all the possible tasks that can be defined by the task description, how to solve it, and environment dynamics. Therefore, we need realistic data that we're gonna encounter, and that data is limited. On the contrary, in context imitation learning, the demonstration is treated as an input, so the network needs only to interpret the provided context and act upon it. So we no longer need realistic data, we need consistent data, that some can be used as the context, some to infer actions from the other demonstrations. And this type of paradigm shift allows us to use pseudo demonstrations that we can procedurally generate in simulation. So they perform semantically the same type of movement relative to objects, but they don't really mean anything. But they perform similar type of pseudo tasks, as we call them. And some of them can be used to define the context as training while inferring actions from the others. And the main point here is that they don't need to be dynamically or even kinematically feasible, because at inference, we're gonna have proper demonstrations that define real tasks and define the real environmental dynamics, such as feasible grasps. The model just needs to understand how to interpret and act upon the given context. So now we have a pretty much infinite pool of training data that you can procedurally generate in simulation. And when you put everything together, you can achieve instantaneous policy acquisition. Here again, I just provide a single demonstration of a task that's never been seen during training, and then the model interprets that demonstration and acts upon it. And it's quite robust to any perturbations. It understands at what stage of the task it is, it understands what it needs to do, and it proceeds to complete the task. So it's quite cool that we can do that, complete novel tasks in different configurations, but they have been the same kind of task that we provide demonstration at inference and then deploy it. So what about generalizing to completely novel objects that never been seen during training and haven't been seen in the demonstrations defined at test time? So for this, again, we rely on our representation. Because we use this graph representation, we can add pretty much any amount of demonstrations we want to the problem. And then we hope that the model can aggregate information from different demonstrations and complete a task. So here I provided a demonstration on the big box, and now when I test it on a different box, it fails because the geometry is different, right? One demonstration is not enough to disambiguate what's actually the purpose of the task. So the model tries what it thinks is the solution of the task, but it fails. Now, when we add more demonstration to the context, so now we provide additional demonstration with a different type of object, right? A small box. So now we are using a context of two demonstrations, one with big box and one with small box. And when we test it with a medium-sized box, now the model can aggregate selectively information from those two demonstrations and disambiguate what is actually the task and how to solve it. And here you can see, it's working on different size and different kind of even shape of the box, still completing the task. So in the previous examples, I provided the demonstrations by manually moving the robot using kinesthetic teaching. But would there be a way to provide maybe those demonstrations, define that context using our hands, which would be way simpler? And the answer here is yes, if we know how to map human hands to state of the robot, so the end effector. And again, this is allowed by the fact the way we chose the representation, how we represent the state. So if we can now map the human hand to robot state, we can define a demonstration, provide a demonstration using hands, and then directly deploy it on the robot. So the whole process is the same, it's just we change the way we provide the demonstrations. Now we provide it using our hands, and the robot can still interpret that demonstration and act upon and complete the task. So it works quite well. In practice, it can be limited by that handcrafted mapping between the human hand and the robot gripper. But for simple tasks such as, let's say, closing a lid of a coffee machine, where only the motion is needed to be interpreted, not very precise, it works quite well. So there's another interesting property of our graph representation, is that there's a clear informational bottleneck in the representation where information from the context and the current observation flows and is aggregated, and that information holds all the relative details to determine the precise low-level actions. And if we somehow could approximate that informational bottleneck using different modality, we could circumvent the need for using demonstration at test time at all. And in practice, we can actually do just that with a small language annotated data set, and we can train a language adapter that tries to approximate that information bottleneck with just contrastive objective. And this allows us to then define the task using language commands. So here I typed in a language command of the task, and then use that approximated informational bottleneck as my context for the model to interpret it and act upon it. And it still completed the task, even though it has never seen this task before. Same with the closing box. So of course, it's quite a hard problem if you try to approximate this using a very small data set of language annotated demonstrations, because then that adapter needs to hold a lot of inductive biases about what the objects actually are. But in practice, it could be enhanced with more capable models, maybe integrating features from foundation models and such. But it already shows quite promising direction that it can understand what tasks there are. So with that, I would like to thank you for your attention and welcome any questions.
Any questions? Yes, please.
When you're showing the demonstrations, is there like an upper limit to the amount of sort of memory it can hold, different types of actions it can perform?
No. So like our graph representation is very flexible. We can add as long demonstrations as we want and as many of them. How many actions we infer at test time is fixed, but that can also be adjusted. Usually what we do is we have a fixed demonstration length, saying that demonstration is defined by that many waypoints, 10 or 16, and that's usually enough to tackle these type of tasks.
And also, if I can add a question, what type of data are you recording during the human demonstrations?
So we represent our state as a graph that embeds the point clouds. So we record the point cloud of the point clouds and the current end effector pose. And from that we can construct this type of local graph that then we use. So point cloud observations and the proprioception information from the robot.
Okay, so in the case that you don't record the robot movements and you use only the human, it's only the point cloud.
It's the point cloud and the estimated
where
would the robot be if my hand mimics the robot.
Okay, perfect.
Thanks, great presentation. I miss actually from where you get invariance with respect to the pose of the objects. Is it coming from the pseudo actions? Is it coming from the graph representation? It's like, yeah, it's unclear to me, possibly.
Yeah, so it comes from two places. So the graph this graph representation holds no information about the global position of each node in the graph. The positions are defined in the edges, and that's only relative. So we get equivariance to the robot and the environment. And then pure generalization to different object placement. That's just pure data randomization.
On the pseudo
Yes.
action representation.
Yeah.
Okay, thanks.
Yes?
Yes.
Yes? Okay, so one question is, what happens if your objects are not symmetrical? Does this affect, so because you always get one point of view from the external camera, I guess. Does this affect the graph representation or anything else in the method? Even though most of the objects that we use, maybe they are symmetrical, but I just wonder.
Yeah, so, sorry, so we do some tasks with non-symmetrical objects, let's say grasping a kettle and placing it. And then you can understand based on the handle. So the nodes in the graph, those green nodes, represent local geometry. And together they define the whole kind of object. And that disambiguates any symmetries. You can understand what way you need to align your gripper to the object to mimic the demonstration, because the information about the geometry is there. So there's no ambiguity about symmetry. Symmetry helps because it can be a bit of an easier problem, it doesn't matter, but theoretically it doesn't cause any problems.
I think the last question. Yeah, thank you.
Yeah, thank you for the presentation, it's very nice. Following up, you said you're generating the points in your graph based on the edges of the objects. Does that mean you're generating them only for the objects or for the whole point clouds? And if it's only the objects, how are you identifying them?
Yes, very good point. So we're using segmented point clouds. We know what the objects of interest are for that task, and then we segment them out and use them just for pretty much efficiency reasons. We could use the full dense point cloud observation of the whole scene, again because the nodes in the graph hold the geometry information. Then the network could decide what parts of the environment are relevant to the task and just ignore everything else. But it would be less computationally efficient. So just as computational efficiency, we segment the point clouds.
Thank you so much.